So we have a lot to discuss, and because only 50% of participants have some experience with magnetometers, let's start with simple theory. So most probably, I'm 100% sure that you know what is magnet. It's a piece of metal which can attract another magnet or another piece of metal. And most probably you saw pictures like this, or you did experiments in school or university, it doesn't matter, that magnetic fields are linked to electrical current. So if you will connect battery to the wire and have a compass close to that wire, when you will close the circuit, arrow of compass will change orientation. Also, you can easily improvise electrical magnet, having just a piece of wire, battery or accumulator, and you can make electrical magnet, which also can attract metallic pieces. So most important here that magnetometry is linked to electricity. It's a very important fact. So magnetometers exist for the thousands of years, actually, in the form of mechanical magnetic compasses, which can be considered as mechanical magnetometers, which shows direction of magnetic field. So magnetic field, it is has two parameters actually: how strong is magnetic field and direction. So in terms of in more strict form, when we measure all parameters of magnetic field, we should talk about vector with some strength, or how strong is magnetic field and its direction. So first device to measure the strength of magnetic field was invented in 1833 by Carl Friedrich Gauss. It is a picture of that device, and it was first having that device became possible to measure not only direction but also strength of magnetic field. And huge improvements in technology, I mean in measuring of magnetic field, were achieved during World War II with the particular aim to hunt submarines. Actually, that application of magnetometers also still pretty standard. You may saw the pictures of airplanes like here with magnetometer sensor mounted on some boom in front or behind of aircraft. So very important to understand that magnetometer measures the magnetic field parameters in the point where magnetometer is. So say if magnetometer is attached to the drone and drone is flying at altitude 50 meters above the ground, it will measure magnetic field at altitude 50 meters above the ground. And magnetometers doesn't have any range. So, or range of magnetometer is 0. It measures the magnetic field where its sensor is. But we can talk about detection range for the particular targets or items of interest. And we will discuss that a bit later. So units to measure the magnetic field called Tesla, or most common are nanotesla, because at 1 Tesla, it's a very strong magnetic field, and except some very specific conditions, we will deal only with the fractions of Tesla. So magnetic field unit also, when we are talking about magnetic field measurements, usually we'll call that parameter magnetic flux density. But it is common to say just magnetic field. We measure magnetic field, assuming that we measure how strong is it and also sometimes direction of that magnetic field. Our planet is also a huge magnet. We can treat it as kind of permanent magnet, but actually it's an electrical magnet, most probably. Interesting fact that magnetic poles are drifting during the time. Here is the map of the north magnetic pole drift between beginning of the past century until 2020. So track is very long, approximately 2,000 kilometers, if I'm not wrong. So when we use magnetic compass, currently it will point somewhere here, but not to the geographic magnetic North Pole. Earth is not ideal magnet. Parameters of magnetic field, when we will measure it around the globe, will differ in different places. So here is magnetic map. Here is magnetic map. You can find link where I took it, and we can see how big is difference of magnetic field in different regions of the planet. So here in the somewhere it's close to Argentina, as I understand, it will be around 25,000 of nanotesla, and maximum is somewhere in Siberia, 60,000, right? So difference is big. And what is also practical use of that world magnetic map? You can use it to check that your magnetometer sensor is working. How you can do that, especially if you use airborne or drone-mounted magnetometer. If you will measure magnetic field at some reasonable altitude above ground to exclude some very local anomalies like from underground metallic pipes, if your magnetometer is working, you will see values very close to the values from that magnetic map, world magnetic map. I can show how it looks. We are in Latvia. It is approximately here. And Earth magnetic field should be something between 51 and 52 thousandths of nanotesla. I will show you measurements. Made using two different magnetometers over our test field close to the Riga. So it is magnetometer number 1, Magnimbus. We can see that in average readings are around 51,600 nanotesla, maybe a bit more. Second magnetometer is Megaro, and we see 51,600. So all magnetometers should show more or less the same value, and that value should correspond to the world magnetic map. So it is quick and easily available method to check your magnetometer without any special equipment. So what we can detect, what we cannot detect. Let's step back to the nature of magnetic field and link of magnetic fields to the electricity. So everything around us consists of atoms. Atoms consist of nuclei and electrons spinning around it. So if in our materials all orbits of electrons, moving electrons are current, actually, electrical current. So if all atoms in material oriented in a random order, in chaotic way, all magnetic fields, very small magnetic fields, created by different spinning electrons in different atoms, will compensate each other. And we most probably will not be able to detect such items, such materials. In opposite, in what we can call magnetic materials, all spins of electrons oriented more or less in the same way, and around item we have combination of magnetic fields of all spinning items in atoms. Looks funny, but it is very simplified explanation of magnetism, but more or less it is true. So we can roughly divide all materials to non-magnetic and magnetic, detectable using magnetometers or not detectable using magnetometers. Very interesting that it is quite hard to make mistake about or guess, can we detect something or not? Sometimes it is pretty obvious. We cannot detect using magnetometers, say, plastic barrel. Obvious, right? But we also cannot detect gold nuggets. Never. Don't try it. We cannot detect many metals like copper. We cannot detect landmines with minimum amount of metals. Very interesting fact that using magnetometer, even from very close distance, we cannot detect turbine helicopter. I personally did experiment with magnetometer, flying with a drone above helicopter. Helicopter was on the ground, of course, with the permission from pilot, in attempt to collect a kind of signature from helicopter. So we were not able to detect it even from 5 meters above helicopter. It was not Robinson, it was bigger 5 seats machine with 2 turbines. It was not detectable at all. Why? Because most of helicopter body made from aluminum and similar non-magnetic materials. And even turbines made from materials which during the processing, hardening, and so on, lost all magnetic properties. The same related to airplanes, unfortunately. Airplanes with different types of engines are also very hard for detection using magnetometers because they use non-magnetic materials in the frame, body, everything, everywhere. And also, unfortunately, engines of airplanes mostly made from non-magnetic materials. Even if we are talking about old piston engines, not turbines, they have a very little amount of ferrous metals. Usually it's a cranks or something like that. We did experiment for the maximum distance of aviation engines detection. So if you are interested, you can ask. I will send you a link for to our report. In opposite, what we can detect using magnetometers. We can detect many types of old landmines in metallic casings, anti-tank mines, and big old anti-personnel mines. But Detection of landmines is not direct use of magnetometers because, unfortunately, most of modern mines have a very little amount of ferrous metal, or they can may not have ferrous metal at all. But using magnetometers, we can detect most types of unexploded ordnance. We can detect metallic pipes, barrels. We can detect something made of reinforced concrete if rebars are steel. We can detect such objects like cars or World War II tanks. I have no idea about detectability of modern tanks because during the processing, armor of modern tank can lose almost all magnetic properties or magnetic momentum, making them undetectable using magnetometers. I never did such tests, but so I don't have any guesses for the modern tanks. But 2 weeks ago, I had a chance to check detectability of the German Panther tank. It is detectable pretty well from few dozens of meters at least. And last slide, kind of educational slide about magnetic sensors and magnetometer payloads. So there are 2 types of magnetometer sensors. Sensors, it's a small device which does black magic of measurement of the magnetic field and sometimes magnetic field direction. And usually such magnetic sensors are very small. So sensor, what we use inside of Magnimbus, it's just a couple of cubical centimeters in size. So we have 2 big groups of magnetic sensors. Total field or scalar magnetometer. They measure how magnetic field is strong. And second group are vector magnetometers. They measure components of the vector. And from components, we can calculate magnitude of magnetic field in nanoteslas, but also we may measure the direction because we know 3 components. And we also can divide all magnetometers by principle of measurements. Very old type, maybe first type of magnetometers were flux gate magnetometers. They have, in principle, very simple design. Maybe you can even try to do it to make it at home. Not very good quality, but it will work. And they called flux gate magnetometers. They have good but not extreme sensitivity, but good benefit of such magnetometers is that they are very robust. So such magnetometers are used in sensors like Sensis Magdron R1, R3, and R4. Second group I can call atomic. They use a bit different principles. I will not dive deeper, but they have sensitivity 10 times better or even more comparing with the flux gate magnetometers. But very important that the difference 10 times or more is achievable in clean laboratory conditions only. What you will see in datasheets, it doesn't have any relation to the real world when you carry magnetometer or magnetometer mounted on the aircraft or under the drone. So in reality, the difference between flux gate magnetometers and atomic magnetometers is just between couple or 5 times maximum. But price difference can be huge. Also, flux gate magnetometers are very robust. They are not sensitive good quality flux gate magnetometers, like in Sensis devices, are not sensitive to the gradients of magnetic fields, where atomic magnetometers can fail. And also they don't have dead zones, so-called dead zones. So it is about sensors. Magnetometer payloads are devices which can attach to drone or to some platform or carry in hands in some cases and used to measure magnetic fields. Usually magnetometer payloads, or in short, magnetometers, consist not only magnetometer sensor, but also additional devices or components like power supply circuits, sensor controller, data logger, or inertial measurement units. So we have sensors, we have ready-to-use magnetometer payloads. And it is necessary to understand the difference because we often got requests about our possibility to supply magnetometer and some link. And opening the link, we see that it is not magnetometer, it is some sensor, which have to be integrated into magnetometer payload to be useful. Principles of detection. So, principle is very simple. When we do magnetic survey, we measure magnetic field or how strong it is magnetic field in the different places of our survey area. Usually we use survey grids with regular lines to have more or less measurements in more or less the same distances from each other to cover by our measurement points all survey area. We measure the magnetic field and look for the variations or for differences. When we see the spots where magnetic field is different from surrounding area, that means that close to that point we have something. It can be a piece of metallic pipe, it can be unexploded shell, it can be anything metallic in most cases. The same principle is used for the minerals exploration, but on biggest scales. So, for example, if we see that in some area, it can be hundreds of hectares, is different from surrounding region, that means that we may have on the ground something like iron ore. So, principle is simple. We are looking for difference. Here is screenshot of the results of actually test run over test ranges of Sensis in Germany. They have a lot of UXO items here. As I remember, it is air bomb, one more air bomb, metallic landmines, shells, a lot of different things. And where we see the spots, that means we have here something on the ground. Here, yes, is air bomb. On the graph, if we will plot the graph of magnetic field, we will see positive or negative anomalies. When we grid magnetic field, we can also notice that anomaly can have positive spot here and negative spot here. Depending on the orientation of the object underground of its shape, we may see only positive anomaly spike up, or only negative down, or both positive and negative. Usually when we see only negative or only positive, we can guess that it is a oblong or cylindrical object with orientation close to vertical. When we see both positive and negative parts, we can guess that our object is close to the horizontal orientation. But it depends on actually many factors. So again, principle is extremely simple. measure magnetic field, and check the difference. That's all. So let's talk about range of detection. Again, magnetometers itself are passive sensors. They measure magnetic field in the point where the sensor is. Range of magnetometer is 0, but we can detect, we can sense anomalies in magnetic field caused by some objects from some distance. And that distance can be very different. It again depends on the actually dozens of factors. When we are trying to understand, for example, our customer is asking us about possibility to find artillery shells or lost airplanes. Best method to check feasibility of such of success of such search is to find information about similar searches, report about some measurements, because predictions actually is very, very complex. And as magnetometry is quite old technology, more than 100 years, we can find information about anomaly caused by different objects at some distances in internet. You can find many reports on that matter. Here is example of such reference information for different types of artillery shells or unexploded ordnance or munitions. And you can see that the detection distance for different types of munitions is very different, starting from just 30-40 centimeters from 20 millimeters caliber shell and up to 3 meters here for 155 millimeters caliber artillery shell. But very important to understand the real, when we are talking about probability of success, we need clearly understand environment in which we will do survey and real capabilities of your system. So we already discussed the difference between atomic and flux gate magnetometers. So usually when I'm preparing for some survey, I consider as a real sensitivity of system equipped with flux gate magnetometer to around 5 nanotesla. So if anomaly from our object is interest maybe plus minus 5 nanotesla, we can detect it using flux gate equipped sensor system with high confidence. If we use much more expensive but more sensitive atomic magnetometer, we can consider 1 nanotesla level as a kind of minimum level of anomaly which we can detect. But we also need to consider environment. If we are talking about tasks like post-conflict battlefield clearances, in many cases, you will not be able to use magnetometers at all because all the field, huge areas can be contaminated with the different metallic scrap, and you will just not be able to discriminate targets. Safe metallic scrap and something dangerous, because in magnetometer data, they may generate very similar anomalies. So if we are, if we are talking about more or less clean environment, like checking of the farm field in the France or in Germany after 80 years of after the war, before, for example, groundworks, we use atomic magnetometer, we can use reference values for 1 nanotesla. If we are talking about some more complex environment, or we just want to be more conservative in our estimates, I would recommend to use 5 nanotesla level. Also, you can see that maximum distance of detection depends on the orientation of the items. So most UXO items have oblong shape or cylindrical shape, and the distance of detection will be different from different sides of the object. So when you plan survey, you cannot predict, of course, orientation of all targets on the ground, and you need to use more conservative values. So in general, I use from that table, that particular table, I use that column. Here you can find a link with information for the maximum detection range for the same munitions and a lot more. What's also very important for the detection ranges? If we are talking about some pretty compact objects, amplitude of magnetic anomaly generated by such object will decrease as third power of the distance between object and sensor. So again, not the depth, not the flight altitude if we use drone-mounted sensor, on the distance between object and sensor. It is almost doesn't matter what is between object and sensor. It can be air if object is on surface, or it can be any soil, clay, water, fresh water, salt water. We can use magnetometers to detect shallow UXO items, for example, in coastal areas. So only distance between target and object, and amplitude of anomaly decreased as third power. That means if we increase the distance 2 times, amplitude of anomaly will be decreased by 8 times. In many cases, probability to detect that object will also decrease it as approximately 8 times. What does it mean? That means that for most of applications, except minerals exploration, capability to have sensor closer to the object is much more important than sensitivity of the sensor. Also, that means that most types of compact objects we will not be able to detect, for example, in the areas of flying over the fields with tall vegetation. I am not talking about tall trees. I am talking about just not harvested fields or bushes or something 2-3 meters tall. If we will return back to the table, we can see that if we are flying at 2 meters, we can detect with high probability only high caliber artillery shells. And we will not find anything smaller. We did experiment to confirm or to see in practice how that rule, I mean, third power the distance works. We took a magnetic analog of 105 millimeter caliber artillery shell and surveyed it at the different altitudes. Half of meter, 1.5, 2, 2.5. Measured magnetic field using drone-mounted magnetometer and calculated what we can expect using rule of the third power. So here are actual values measured using magnetometer. Here are calculated values. So we used the measurements from the distance half of meter as a reference point. We took the same value, and for 1 meter, also measured value, 407 nanotesla. For estimated anomaly, we divided this value, 4,500 nanotesla, by 8, and get absolutely the same value. For next altitude, 1.5 meter, we have a different values. My guess it is because all experiments with airborne system with airborne magnetometers are not very clean, because we may have some errors because of not very even, not the same lines exactly over the object. But at 2 meters, we have very good match again, and 2.5 also very good match. Why it is important to know that rule? If you have reference values for some distances, you can calculate, for example, for 1 meter or for 2 meters, you can easily calculate or estimate amplitude of anomaly from the same object, from the closer distances or from the longer distances. So for that particular object, 105 millimeter magnetic analog of artillery shell, we can estimate that maximum distance of robust detection, 5 nanotesla, is between 4 and 4.5 meters. And at 7 meters, we will not be able to detect that target at all. So we finished with the theory, with the discussion of the detection ranges. And let's review quickly the possible applications. At the moment, most popular application of magnetometers is minerals exploration. That application is based on the fact that many types of valuable minerals disturb Earth magnetic field and cause the magnetic anomalies detected even from relatively high altitude above the ground. Normally, such surveys we can do from pretty high altitude to 20, 30, 50 meters with big separation between survey lines, because we are looking for something which is huge, heavy and deep on the ground. So say our minerals body is 200 meters on the ground. It is almost doesn't matter at what altitude we will fly. Distance will be 220 meters or 240 meters. Typical users for such of magnetometers for such application scenarios are mining companies or service companies who are working for mining companies. And normally for such applications used atomic magnetometers, because such anomalies can have very, very small amplitude. Sometimes, unfortunately, it can be fractions of 1 nanotesla below some comfort level of detection, and some quite complex data processing precisions can be necessary for such scenarios. Second popular scenario is searching for unexploded ordnance and landmines in metallic casings. Typical users are government organizations or non-government, non-profit organizations like Hala Trust or Norwegian People Aid, who do post-conflict periods around the world, or service companies who are working for that organizations. And typical magnetometers are Fluxgate, Sensis Magdron R1, R3, R4, or also Magnimbus. Magnetometers which are popular for minerals exploration, like GEM system, GSMP, or Megero, are not very good for such purpose, because they're mounted under the drone using ropes. Standard ropes for Megero are 3 meters. Standard cable length for GEM systems magnetometer is 5 meters. And for such application, you already know, it is very important to fly as slow as possible. So ideally, just few 3-5 dozens of centimeters above the ground. So drone should follow terrain with very high precision, and unfortunately, magnetometers mounted on the ropes with every change of speed, direction, acceleration of the drone will start to fluctuate, and you will, in magnetic data, you will seek host targets or you will miss real targets. So for such applications, better option are magnetometers with hard mountings on the drone. Second application is trump metal lost ground engagement tools detection. So I mean searching for the pieces of metals in stockpiles. Such pieces of metals can be serious problem when they do. They will go through the transportation belts, crushers, and so on. They can damage equipment, and they can cause multi-million losses. I saw. I was spectator of the almost 3 days stop of the gold open pit mine in Pacific region, and 1 day cost was around 1 million, as I remember. So it can be a huge problem. Technique is absolutely the same as for UXO, because we are looking for the same pieces of metal, quite compact, concentrated pieces of metal. Very similar task as well, locating of buried infrastructure like metallic pipes, shielded cables, old shielded cables, because modern cables often shielded using non-magnetic materials, and electrical cables under load. So usually cables made of copper, but if they are under load, they can be detected using magnetometers. Typical magnetometers are the same as for, actually any magnetometers can be used for such type of works. In principle, technically it is very simple, and data processing also is very simple for such surveys. Next big group, popular, for example, in North America, where there are dozens of thousands abandoned wells. And infrastructure is detection of abandoned wells and infrastructure. Also very similar to the previous application, very simple technically. For example, abandoned wells often cause so bright anomalies that you can detect them usually actually using magnetometers built in your smartphones. I am trying to show my smartphone. So I can detect using 6 meters long piece of metallic pipe with diameter around 15 centimeters, as I remember, from distance up to 3 meters, just using smartphone. So some of tasks can be very simple, and for such tasks, any available type of magnetometers can be used. And archaeology, typical users are service companies and universities. Usually they use financing from grants. And here, main argument for the magnetometers or sensor selection are budget constraints, unfortunately. Why unfortunately? Because some archaeological points of interest, objects interest, for example, backfilled trenches or compacted floors in the old buildings or something similar will may cause very weak anomalies, like for the minerals exploration, just fractions of nanoteslas or 1, 2, 3 nanoteslas. And in theory, they need maximum sensitivity. But we saw that in many cases, main factor is availability of the funding. Yeah, here you can recognize that QR code and see a bright case study about a combined use of drone-borne and towed marine magnetometer to detect pipelines, cables, and presumably UXO items in coastal area. It's very interesting project when where airborne magnetometer was used in survey in tidal area, and where it was not possible to use towed magnetometer, and towed magnetometer with the magnet boat in the deeper areas of that survey zone. Very interesting case study. So what we propose, we propose not only, of course, not the sensors, not only even not only magnetometer payloads. We propose systems for the commercially available drones. So you can buy DJI drone from nearest DJI reseller. You can buy a compatible American-made drone, for example, Inspired Flight or Whisper in North America, and mount magnetometer system on it. Magnetometer system consists of magnetometer payload, onboard computer, which for some types of magnetometers works as data logger. For some types of magnetometers, it implements true terrain following or capability to follow terrain using radar or laser altimeter. We also proposed obstacle detection sensor. It is clear that when we are flying at altitude just 1.5 meters above the ground, all bushes, fences can be dangerous for flight, and better to have a capability at least to stop our drone before he will be crushed. We provide flight planning software and flight management software, training, support, and also we provide or recommend software for data processing. It will be last step, last slide of my presentation. So what our main sensors? We manufacture own magnetometer payload. We called it Magnimbus from Harry Potter, inspired by Harry Potter. Inside of Magnimbus, we may use one here and here, or two here, Q-spin sensors. Q-spin, it's an American manufacturer of atomic magnetometers. They are very small, very light, and extremely sensitive. We supplied that system in the single sensor or vertical gradiometer configuration. And workhorses, magnetometers manufactured by our partner Sensis from Germany. They have a range of magnetometers R1 with single magnetometer, very similar design with Magnimbus, with automatically foldable arm. R3 with 2 magnetometers, and R4 with 5 magnetometers. Sensors are absolutely the same. Detection capability in theory the same, but in practice with R1 detection capability is maximum, because on the foldable arm you can fly closer to the surface without crash risk. How to select a better sensor if you want to have a workhorse from Sensis is actually environment in what you will work. If we are speaking about kind of fields, prepared fields, maybe better choice is R4 with 5 sensors, because you can collect very dense data. Here, distance between sensors is just 50 centimeters and covering pretty wide line in single pass of the drone. So in opposite, R1 collects only one line in single pass, but you may have maximum detection capability, because practically over the fields like here, you can fly without any risk for the drone with a sensor to ground separation just 20 centimeters. In regards of missions planning, of course, planning for every type of sensor, even for different cameras, will have some specifics. Magnetometer missions also have specifics. Main point that if for the most popular airborne sensors like cameras or lidars, normal flight altitude starts from 80 meters. For magnetometers, practical maximum, even for manual exploration, is around 50 meters. normal altitude of the trees in Europe, for example, in Poland, is around 30 meters. In some regions, like Papua New Guinea, in the jungles, I saw trees up to 60 and maybe 70 meters tall. So, main issue of magnetometer surveys is relatively low altitude, even if we are doing surveys for minerals exploration. If we are searching for the man-made objects like World War II tanks, missed aircrafts, we should fly at couple of dozens of meters above the ground. If we are talking about very small objects like unexploded ordnance, sometimes we need to fly actually as slow as possible, because after a couple of meters, we will miss almost all possible targets. What we propose here, for the relatively high magnetometer surveys, in our software, in UgCS Expert, we have few groups of functions designed, first of all, for magnetometer missions. First, that function actually was introduced more than 6 years ago, when we got first customers flying with magnetometers connected to the drones on ropes. We implemented possibility to add to our flight plan overshot segments with reduced speeds. They are here. So border of our area, what we want to survey is here, and you can see segments outside of our area. So it is to give possibility to the drone to reduce speed, slowly make U-turn and accelerate, slowly accelerate to enter to the survey line with stabilized flight parameters to prevent pendulum motion of the sensor hanging under the drone. It was very first feature in UgCS to support magnetometer survey. Couple of features were added recently. It was trajectory smoothing. Magnetometers, especially magnetometers connected to the drones using ropes or cables, are very, very sensitive to the stability of the sensor. So drone should fly as smooth as possible. For that, we introduced additional 2 parameters for the mission planning: maximum gradient of the slope in percents, meaning, for example, if we specify 30%, at the length of the 100 meter, drone can climb or go down just for 30 meters, 30% of the distance. And we introduced the possibility to specify minimum gap of the temporary elevation depression or decrease, because in many survey areas we can see something like canyons, like here, and we don't want to allow our drone to dive into such canyons and next climb up. First of all, it will be useless, because after such maneuvers, our magnetic data will be absolutely useless, and in many cases, it's just dangerous for the drone. So we introduced the 2 parameters to make flights as smooth as possible. Also, what was introduced recently, we introduced direct support for digital surveys model. So nowadays, most of the flight planning software packages support DTM, digital terrain model, to plan flights at the constant elevation above ground surface. But for magnetic surveys, when sometimes we had to fly, say, at 5 meters above treetops, we need to have a means to validate, to check the flight route for the safety. So in UgCS, you can load DTM, digital terrain model, and you can load DSM, a secondary layer. And UgCS will visualize ground, what is on the ground above the surface, it is green, and our flight track, and calculate distance not only between our flight line or trajectory and the ground, but also it will check the distance between our flight line and the all objects present in digital surface model. 2 weeks ago in Poland, when I worked with the beta version of UgCS with the first implementation of DSM support, we flown at just 5 meters above treetops, and it was pretty safe. So old feature is terrain following according to DEM, digital elevation or digital terrain model. Actually, UgCS was first software on the market with that support back in 2013, in very first version of UgCS. And also UgCS in combination with SkyHub and Altimeter supports true terrain following for DJI and ArduPilot drones. True terrain following means that drone constantly will be altitude of the drone will be constantly adjusted according to the real-time readings from altimeter. So it makes possible extremely low-level flights, say with the sensor level clearance just few dozens of centimeters. We started to work with magnetometers back in 2017, 7 years ago. So we quickly came to idea that we need own test range to test different magnetometer setups, workflows according to the known anomalies. Our first partner or supplier of magnetometers was Sensis. We found that Sensis also has great test field with different UXO and munitions. Now we have a huge, okay, not huge, but bigger in the world public collection of the magnetometer data collected over known targets. So first collection is data from our own test range. So what we have here, data from many types of magnetometers. Magnimbus, Sensis, GEM systems. GEM systems, that data set is for terrestrial survey, to use it as a reference. Results of funny experiments. For example, this data set is internal compass data extracted from drone autopilot without any external additional sensor. It was very funny to see that we can detect biggest targets without any additional sensors, just flying drone over such targets. I suspect, for example, that we can detect abandoned wells in United States just flying drone without magnetometer. Magnimbus in gradiometer configuration. Here we can see the benefits of gradiometer. We can detect smaller, weakest anomalies, or at least to make it more contrast. Data collected, my smartphone hung it under the drone. Very interesting that we detected all pipes in our test range. And Megero, GSMP, all models of Sensis magnetometers. So you can not only see pictures, but for all surveys we provide raw data, we provide description of the survey. You can use the data for free, but if you will use our data in some publications, please add reference to SPH Engineering. Second public data set is from Sensis test range called Sensis GeoMil. Here we from Census Geomil we have data from of course all models of magnetometers manufactured by Census, and also they allowed us to run Magnimbus, our payload, over the test range. So again, the same in attachments you can find all data, and yeah, you can compare the anomalies with the real targets. Here we uploaded brutal pictures of all targets in the test range. And you can compare the anomalies and real targets. Yeah, and last topic, short topic, data processing. Why short topic? Because data processing actually should be biggest topic when we are talking about magnetometer surveys, because in most cases it may be most complex part of entire job, especially if we are talking about minerals exploration. So we recommend at the moment two options for the data processing. Option number one, using Geosoft Oasis Montage. I love Oasis Montage. I use it almost every day. But he made me crying when I just started to learn it. So if you want to be able to do with magnetic data everything what is possible in theory, you have to learn Oasis Montage. But please be ready to invest at least a couple of months. To simplify a learning curve, we prepared Oasis Montage crash course. And also we have a couple of webinar recordings about data processing in Oasis Montage. Here is a course with exactly 99 steps, but every step is very simple, understandable, and it is described here with screenshot of all Oasis Montage user interface elements. So you can request, if you don't have Montage, you can request trial version from Geosoft. Currently it's a Bentley. You can download data what is used in that crash course. It is data from discussed public data set, and reproduce the same. So from the data import and till the markings of the targets. Intentionally, I use it here when I prepared that crash course. I use it very simple, or as simple as possible workflow or approaches, which don't require background of professional geophysicist with university background. So I should note that learning of Oasis Montage requires time, but you will be rewarded, because using Montage, you can do with your data absolutely everything. Second note, that Oasis Montage has a reputation of extremely expensive software. It is not true in general. For the magnetic data, and what I use it in my crash course, and actually what I use every day, it is a set of functions included in a basic Oasis Montage license called Oasis Montage Essentials. It cost in different regions, they set a different prices, but in general, it is below $5,000 per year. They sell subscription. So considering the cost of entire system, of the expenses for the learning curve, for the cost of jobs, how much you can bill for your customers, 5,000 per year is not too much for the most powerful software for that purpose in the world. second option, it is available right now in the form of beta version, and I have a huge hope that we will release it in December. In January maximum, it is our software called GeoHammer. You can download the current beta version from here. So that software exists for the long time, more from 2018. Initially, it was created to pre-process GPR data, not magnetometer. But as we see many new users of magnetometers technology, we decided to implement very simple software to lower the bar, entry bar for the new users of magnetometers for the simple scenarios. Simple scenarios, I mean, at least initial assessment of UXO data, utilities, trump metals, environmental surveys, and similar, when we are looking for the relatively big metallic objects. So how it works? Yeah, I will not demonstrate the data processing in montage because we need at least another 1 hour, but I can quickly show data processing in GeoHammer for the simple scenario. So what we need to do, we need to take magnetometer data and drag and drop into GeoHammer window. So next step, we can cut the survey lines, our flight track, to get only survey lines. And we can try gridding. We can adjust palette. And yeah, that's all. Of course, it depends on the quality of data. Here, quality of data is very high, and amplitude of anomalies caused by our targets, our metallic pipes and 4 metallic barrels here, is quite high. I can show you something different. UXO, for example. It is data from Sensis R4 magnetometer collected over Sensis GeoMill test range. Let's try gridding. Yeah, also not bad. So we can insert marks. We can export marks into KML files. We can export our generated magnetic map into geotarget GeoTIFF file. So very simple software with a very minimum set of functions required for the standard simple cases for magnetic surveys. Almost all possible cases except minerals exploration. To process the data for minerals exploration, you may use GeoHammer just to check that you have data which looks as useful, but for data processing, you will have to use more sophisticated tools like Oasis Montage. Okay, let's look at questions. First question, don't you consider to develop geohammer for Mac-drone RFO? Not necessary for anomaly visualization, but just to view graphs of collected data for in situ QC reasons. I demonstrated geohammer with R4 data. That data is from R4. So, what should be direction orientation of sensor during survey? East, north? So, that usually that question, that concern is linked to the dead zones and to minimize heading error. So I didn't explain what is heading error. In short, when we take the magnetometer sensor, for example, this is my, you will not see, right? Okay, if you will take magnetometer sensor, start data recording and will slowly rotate the sensor around z-axis. We will get different values depending on the sensor orientation. That phenomena called heading error. For different models of the sensor, it can be quite big, up to a few nanoteslas. So to minimize heading error, usually you need to fly perpendicular to the direction of the magnetic, the direction of the vector of magnetic field in your survey area. You can find that information in World Magnetic Map, or you can find more detailed information in many sources. So perpendicular. If you don't have such additional information, you need to fly east, west, and back, not north and south. Or if you use sensor like GEM systems, which is just cylinder hanging on the rope under the drone, best recommendation what I can give you is to fly with a constant heading. So to not make your turns at the ends of survey lines. So in such cases, your heading error will be zero and risk to went into dead zone because of U-turns will be also almost zero. Next question is, what are the biggest challenges operators face during magnetometer surveys and how can this mitigated? Can you recommend any specific software or workflows for processing and interpreting magnetometer data? A lot of questions, actually. Let's start from the first question. Biggest challenges are usually logistics, because in many cases, magnetic surveys should be conducted in remote areas. I participated in surveys when we were delivered by helicopters to the survey area and used drones here just to save money for the end user. And costs of logistics and all linked expenses, time spendings, and so on can be extremely huge. But if we are on site, next challenge is a necessity to fly low. So for the manual exploration, usually it's a few dozens of meters, but we still have a risk to hit treetops, and we need to follow terrain. In overall, that means that we need to have precise elevation data, both DTM, digital terrain model of the bare ground, and DSM, preferably. So nowadays, it is pretty simple requirement to achieve, but it requires pre-survey of all survey area, what you want to scan with magnetometer using LiDAR. So from LiDAR data, you can generate both digital elevation model, terrain model, and DSM, and use in UgCS to plan low-level flights. For the almost all other types of survey, you will need to fly extremely low. So here drones should be equipped with terrain following systems. Can you recommend any specific software or workflows for processing and interpreting magnetometer data? Actually, I already answered. Most universal software on the market is Geosoft Montage For the simple cases, we recommend our software GeoHammer. And in regards of interpretation, it's 100% depends on the application area. Of course, interpretation for the UXO and Trump metals more or less the same, but there is a absolute difference between minerals exploration and UXO and processing workflow, except very basic steps like filtering also will be very different. So it's topic for different webinars for every single application scenario. So for companies looking to add that capability, it was here were additional questions, colleagues.
I have already contacted about pricing and everything. So no worries. The last question was about the pricing.
Okay. Next, could we find the depth of anomaly? There are methods of the estimation of the depth and even weight of anomalies. We had a webinar on that topic. You can find a webinar using keywords like processing magnetometer data in ASIS montage on our site. And it was joint webinar of us and Sequent. Now it's Bentley. And here is explained algorithm how to estimate depth. So some software packages like Sensis Magneta. Sensis Magneta, it's a reporting software, mostly for UXO surveys. They have a quite simple to use function to estimate the depth of objects which having cylinder as model of the object. Because that software is oriented mostly for UXO surveys, but also there are few methods to estimate depth based on the different approaches. Maybe best and simple description I found on the Gem System site. You can try to Google. If you will not find, you can ask me. Also, if you have gradiometer, like Magnimbus gradiometer, or you collected the data at different altitudes, you can also data from 2 layers to estimate the distance till the target. It's a pretty simple equation. Next question is, what is the positional accuracy from 20 meters? You mean you are flying in 20 meters, you detected some anomaly. I would estimate as 20 meters. So, because if you are able to detect anomaly from 20 meters, you will see some not sharp peak in magnetic data. You will see some smooth over the some distance. If you're detected something from 20 meters, most probably comparable anomaly will have comparable length in your magnetic data. So estimate your positioning or position estimation for the targets at the same as the flight altitude, more or less. Next question, it is easy to calibrate the magnetometers. So magnetometers, what we use, what we propose, don't require magnetometers calibration at all. If they were not damaged during the crashes or transportation. So most damages for our equipment we had during transportation, not during the, not because of the drone crashes. They don't require calibration, but there is a technique how to remove heading error from the magnetometer data. I explain it. What is it? So usually results of the hidden error you may see in magnetometer data as stripes. So there is a technique how to remove results of heading error from magnetic data, collecting heading error compensated data. In short, you need to conduct flight at reasonable altitude starting from 50 meters above the ground. Normally, most manufacturers recommend clever leaf pattern. It is to collect data in 8 directions. And having the data, you can eliminate, you can calculate delta in the average value for all directions, and you can eliminate heading error from your data sets. Sometimes process of collecting such heading error compensation data called calibration, but it is not calibration of the sensor. Next, can we say base station and a rover jointly gradiometer? No, gradiometer. Usually, when we say gradiometer, we are talking about sensor which has two moving sensors, one above other. Sometimes we can talk about horizontal gradiometers, like in census sensors when we have multiple sensors along the horizontal bar. But normally gradiometer means two sensors, one above other. So they don't replace base station totally, but if we are looking only for the variation of magnetic field, and if we have radiometer, we don't need base station, because all sources of external magnetic fields, which are usually quite far away from our drone, will make the same influence on the both sensors, lower sensor and upper sensor. We are interested only in the difference between measurements. But if we are talking about large-scale surveys, for example, for minerals exploration, where we need to join the data gathered during some long time, we may need magnetic base station. Next question. Is magnetometer sensing directional or omnidirectional? In other words, do you need to point it to the source? Again, magnetometer measures magnetic field in the point where sensor is. So target or source of anomaly can be everywhere in any point around our magnetometer. So it is kind of omnidirectional. We are interested in using a drone mag to search over shallow water, approximately 2 to 10 meters deep, conducting archaeological surveys. If budget was not an issue, what mag would you recommend? For such depth range, I would recommend marine towed magnetometer, most popular magnetometer manufactured by Geometrics. You can find how it works, data from it in case study, what I mentioned in my presentation. Yeah, scan this QR code and you will see published case study, and I would recommend that towed magnetometer, not the drone. It is wrong to perform a simple interpolation of the data secured with Surfer, any specific programs required for processing. So in case of good quality data, very strong anomalies, you can use even Microsoft Excel or Google Sheet to find anomalies in your data and to see coordinates corresponding to that anomalies. So I tried to use Surfer many years ago. As I remember, you can use simple filters like low-pass filter, but I don't sure that you can use pretty standard for magnetometer data operations like GNSS lag compensation, but I may be wrong. So if Surfer works for you, it works for you, you can use it. So in extreme cases, you will need Oasis montage, of course. Which magnetometer do you suggest for archaeology survey? So best magnetometer what you can buy for your budget. I don't recommend to use any magnetometer with cords or ropes, because for archaeology you will need to follow terrain with high precision, and such magnetometers, I mean Megaro, GEM systems, GSMP, will start swinging. You can, depending on your budget, you can use Sensis, Magdroner 1 maybe, or Magnimus, if your budget allows more sensitive model. And also Magnimbus, you can order in vertical gradiometer configuration to detect smaller targets, or at least to simplify data processing. You saw the difference in our public examples. I can show again. So it is data from Magnimbus in single server configuration. Here we see targets, but they are not very contrast or bright, right? Changing a little bit on the data processing, spending more time, we can make them brighter. But in gradiometer configuration, we can see the same or even more here. Let's compare in that area. Yeah, no, we see the same, but in gradiometer configuration, we may spend much less time and at least not to miss small weak anomalies if we don't have infinite time for processing. So it's a benefit of gradiometer. In terms of capabilities to detect, if gradiometer single sensor configuration uses the same sensors, they're the same. Difference will be in the data processing mostly. Yeah, and possibility to use the magnetometer close to the sources of external electromagnetic, usually electromagnetic fields like power lines, settlements or something. Next question. If I'm not mistaken, the induced magnetic field depends on the direction of the Earth magnetic field changes with the latitude. Do you take this into account while measuring or in the processing part? You are absolutely right. There is a possible step in magnetic data processing called reducing to pole, which normalized magnetic data, make it in the same as it was right above the north magnetic pole. Do you take this into account while measuring or in the processing part? So I try to use it for our typical data sets. I mean UXO, archaeology, and so on. I didn't find any benefits or data improvements as a result of applying of significant benefits, say, of applying that additional processing step. Next part of the question also, is there a way to isolate the induced magnetic field from the remnant one? For the range issue, there was in one slide, except for minerals exploration. Why is that? Never tried. So I should say that my profession is software development. So I am not professional geophysicist. We can ask our geophysicist, Professor Yanis Karos, to answer that question. Most probably yes. So for the range issue, there was in one slide, except for minerals exploration. Why is it? What slide do you mean? For most applications, except minerals exploration, lower flight altitude plays a larger role than magnetometer sensitivity. Most probably you mean here. So for minerals exploration, typical flight mode, you fly with the long lines, and you can fly that lanes to have them pretty smooth with a constant speed and minimizing the changing of the acceleration, speed vector, anything, to collect as clean data as possible. Having such flight envelope, you may achieve practical sensitivity of the airborne magnetometer up to the fractions of nanotesla. In such and also magnetic anomalies in manual exploration can be very long and can be very smooth, fractions of nanoteslas along hundreds of meters or sometimes kilometers. For such application, peak sensitivity of the magnetometer is important. In opposite, for almost all other scenarios like UXO, archaeology, utilities, abandoned wells, you need to follow terrain to maximize detection capability. And proximity to the target is more important than sensitivity of the sensor. And anyway, when you follow the terrain, sensor measurements will fluctuate even if we will have absolutely sterile neutral magnetic environment, no targets, no anomalies, just because of the changes, even little changes of the orientation of the sensor. So in terrains like I demonstrated in the flight planning slide, like here, most probably you will never achieve sub-nanotesla real sensitivity because terrain is very raw. But here sensitivity may play, for manual exploration, sensitivity may play huge role. Oh, next question. Which Oasis montage models do you use? Normally I use Essentials, basic model, basic license. Also, I used UXO length survey in attempts to estimate, to use the functions to estimate the depth and size. But normally, essential Oasis montage essentials is good enough for most of purposes. Next question, which magnetometer you showed is the most sensitive? So, Magnimbus, Magero, Gem Systems have more or less the same practical sensitivity. Sensis magnetometers have 2-5 times, depending on the flight envelope, less practical sensitivity. But in case of raw terrain and very precise terrain following, even flux gate magnetometers can collect better data comparing with the Magero or Gem Systems. But Magero is quite universal atomic magnetometer. It joins the high sensitivity of atomic magnetometer and hard mounting of Sensis sensors. It has automatically foldable or unfoldable arm for the sensor. Next question is calibration and compensation flight procedure for the vector magnetometers. No, you don't need to do. Okay. Sensis in their old user manual had description of compensation data collection procedure. As I remember, in latest version of their user manual, they removed that paragraph. As Sensis guys told me, it is very rare situation when applying of compensation data for vector magnetometer will bring benefits, but quite often you can lose real anomalies. So currently they don't recommend use any compensation procedures. They recommend by default to use very simple processing sequence using running average, calculation of the running average. That option is active by default in Census McDrone data tool. Next question, how clean is the initial data recorded? What physical environment might affect the data quality? So clean, what we usually see in the, what types of noises we usually see in magnetic data. So we see relatively high frequency noises from drone motors. Frequency of that noises is between 30 to 50 hertz. And as most of the modern magnetometers have sampling frequency above 200 hertz, you can easily remove drone high frequency noises from motors with in one simple step, I mean applying of low pass filter. It is simple, understandable, and pretty safe filtering procedure. Second type of noises which presence in all data sets, it's sensor movements induced or platform movements induced data noises, including heading error. So heading error can be compensated at least partially using known procedures which require usually collecting of compensation data. Bad thing that platform-induced noises have very low, not regular frequency. They have a floating frequency as drone moving, for example, during the terrain following. So it is why smooth flight trajectory and having sensor not on the row in case of very rough terrains, it's very important to not have such type of noises. Third typical type of noises is noises from the external sources like power lines, railroads, or something similar. They can be removed using sometimes ground station if such sources are very far away. If they are quite close to our survey area, we can use vertical gradiometer. So what, there are also the time variation, diurnal variations of the magnetic fields. They usually can be removed using magnetic base stations or results of magnetic soil storms. What physical environments may affect the data quality? So actually, where you work in the presence of external magnetic fields or during magnetic storms, for example. So to eliminate such external sources, you need base stations or gradiometer, or both base station and gradiometer. So are there special requirements to fly over water? No, absolutely. So we recommend to use terrain following system to have predictable safe altitude over water. The important fact, if you are flying in the areas with a huge difference between low tide and high tide, terrain following becomes absolutely mandatory because for the modern drones with a flight time 30-40 minutes, the difference in tide level can be, say, 1 meter. If you are flying very low, flying with just preset absolute altitude can be too dangerous. So better to use the drone equipped with terrain following system. Next, does magnetic storm affect magnetic anomaly? Yes. In some cases, magnetic storms can be very strong and can ruin the data. So actually, what you can do, you can have a magnetic base station. It is stationary magnetometer, which should be bit outside of your survey area in magnetically clean place, far from the sources like power lines. So after the survey, you will just deduct magnetic base station data from your magnetometer data, and you will have a difference, clean it from the magnetic storm effects. It's absolutely standard procedure supported by all data processing software, yeah, except GeoHammer, because GeoHammer is for simple cases. Can you share the drone.js map link with the UXO pictures embedded? You will have a link in the presentation. So you will find UXO items pictures in the images by the link to to GeoMill test range. The next question is, can any of the magnetometers used with the drones provide the value of the total magnetic field measured by both probes in the output file, or do all of them only provide the gradient? All gradiometer systems, including Magnimbus and Sensis magnetometers with multiple magnetometers, provide data from every magnetometer sensor in the system. In case of Magnimbus, gradient should be calculated in post-processing. In a case of Sensis sensors, they just provide readings of every sensor on the sensor bar. So you will have not only gradient, more precisely in the raw data, you will have data from every sensor, and gradient will be calculated in post-processing. Next, I use the GEM atomic magnetometer. We mainly use it in the field of minerals exploration. The main focus of this presentation is UXO. I think you use corrections for IGRF and duration when you output the analysis diagram. Are you making any other special processing or corrections? No, I didn't use IGRF or variations corrections in presented results. In most of the magnetic maps, what I demonstrated, we use very simple approach, calculating the running mean value across the lines and calculating the delta, because running mean and current value. That method, very simple, straightforward methods, allows to highlight local anomalies. So I didn't use processing steps what you mentioned. For the UXO, they don't provide any additional value. Next question, how the heading obtained in the Nimbus compare with the R2? R2 does not exist. Maybe you mean R3 or R4 or R1. So in Magnimbus data, we log values for heading from drone. So it is heading of the drone, actually. Next question, how to filter or remove large objects or disturbances in data processing without losing information on smaller objects. I don't know the robust method how to highlight anomaly from small targets at the background of big target, actually. It is main of the fundamental issues of the magnetometry. So say you have a big artillery shell and small artillery shell in the more or less the same coordinates, one above other. So you will see kind of combined anomaly, and I don't know robust methods. Next question, on an oil well that is abandoned and the casing it cut off and sealed at approximately 10 meters, and the casing is 1000 meters, and that compared to a casing that is 500 meters, which could give you better data. Drone would fly at 3-5 meters above ground. Casing is steel and straight 90 degrees to surface grade. Richard, such casing you can detect even from 50 meters. Don't worry about it. you can hang your smartphone with the free magnetometer data recording software on your smartphone, and you will be still detect your targets. I saw the data from smaller, much shorter casing detected from 60 meters, and anomaly was still few hundreds of nanotesla. So maybe such scenario, it's the most simple scenario for the detection using magnetometer. So for such direct answer on your question. Sorry. In first case, amplitude of anomaly, I mean almost 1 kilometer long casing at the cut at below 10 meters under the ground, and second 500 meters long casing. I suspect that in first case you will get bigger anomaly, but will be interesting to check. If you can share with us some data for oil wells, it will be great. I have few data sets, but it is always interesting to see more, especially if you know the parameters of the casing. One more, can I use it also for morphometric analysis and active tectonic estimates of normal fault scrubs? It depends. So I'm not geologist. So usually faults produce visible magnetic anomalies. I even have data for collected in Poland 2 weeks ago, which were interpreted as faults, geological faults. So in common answer is yes. And last question. How you use it in groundwater exploration surveys? Have you used it in groundwater exploration surveys? If yes, how accurate were the results? So magnetometers are not suitable in general for groundwater exploration. Typical geophysical methods are resistivity surveys. They require electrodes inserted into ground, or second method called transient electromagnetic surveys, but not magnetometers. Not magnetometers. Whew. That's all.